Well, let's get started here. So, let's see. So, we were talking about this thermal response here when we left off last night. So, the reason how this relates to aviation is, and weather is basically the land is much more, much more susceptible to retaining heat variances in temperature than water is. Water, it takes a lot longer to heat up the water versus sand. So, or land. So that's why we're going to see things like, sea breeze and land breeze and different times of the day, or we'll see convective activity, all those kinds of things. And it's due to the little amount of heat that it takes to warm up the land. So this graph right here just shows the comparison of water and sand after heated with 4.18 joules of heat energy, right? Both start at 25 degrees, and after the test, the water only bumps up a degree, whereas the sand will bump up 5 degrees. So it's comparing to this, this is why the beach sand is hotter than the water on a sunny summer afternoon. So, like it says here, the difference in specific heat capacities is one of the primary reasons why temperature of a body of water, such as a lake or ocean, is less variable with time than the surface temperature of land. Water heats up more slowly than land during the day and during the summer, and cools down more slowly at night and during the winter. Thus, a body of water exhibits greater resistance to temperature change, called thermal inertia, than does a landmass. So that's going to affect the weather that we see in seasons a lot greater. We look at San Francisco here, and the variation in temperature throughout the 4 different seasons is going to vary much less than, say Kansas City, and that is due to the proximity to water. It's like San Diego. San Diego maintains, 70 to 90 degree temperature pretty much year round, whereas the variance of even Salt Lake is going to be pretty similar to this, where it's 30 degrees Celsius, which translates into like a 50 to 70 degree swing in temperature here. So temperature variations with altitude. A lapse rate of temperature is defined as a decrease in temperature with height. So do you guys remember me telling you when we started talking about ISA and the standard lapse rate? Well, here it is. It's stated that the temperature decreases at 6.5 degrees Celsius per kilometer, or 3.57 degrees Fahrenheit per 1,000 feet. So this translates into 2 degrees per 1,000 feet. So 2 degrees Celsius per 1,000 feet. In the standard atmosphere, and that's the standard atmosphere, but since this is an average, the exact value seldom exists. In fact, temperature in the troposphere sometimes remains constant or even increases with height. So we have, basically this leads into two different types of lapse rates. We have dry adiabatic and wet adiabatic lapse rates. So atmospheric surrounding. An atmosphere surrounding is simply sounding, or atmospheric sounding, sorry. Or simply sounding is a plot of vertical profile of one or more atmospheric parameters such as temperature, dew point, or wind above a fixed location. Soundings are used extensively by meteorologists. So this is, like the weather balloon. They take a snapshot, basically, of the atmosphere in a very specific location. So the isothermal layer, it's between so what it's saying is the isothermal layer is within the atmosphere where the temperature remains constant with height. Okay, so there's a thermal layer, and it's similar to water. Water also has an isothermal layer. But there is a point at which the temperature will remain constant for a period of time. So these are all things that we have to take into consideration when planning a flight. So inversion, like I stated in a previous class, this is something that I want you guys to have memorized. But basically all it is where hot air traps a layer of cold air underneath it. And so rather than the temperature decreasing as you gain altitude, it increases for a period of time. The inversion will trap things like pollutants, dirt, dust, things like that close to the surface. So you can see here, this is what surface-based inversion, so Salt Lake, this is what it looks like. We gain temperature as we ascend, but then we lose temperature. If we have an inversion aloft, it just changes the altitude in which the inversion occurs. Okay. So let's talk about water vapor. So we've talked about, this thermal, talked about the heat transfers, things like that. The other thing that we need to develop clouds and storm systems would be water vapor. So it's the gaseous form of water and one of the most important of all constituents of the atmosphere. So even though it only constitutes a small percentage of the Earth's atmosphere, it's still a big part of all weather in the tropopause, or in the troposphere. So this is something that you learned in elementary school, the hydrologic cycle. We have different types of evaporation, condensation, transpiration, sublimation. All of these are, you know, it's the water cycle, like it says there. So all very important in our weather patterns here. So evaporation, it's when the water turns from a liquid to a gas. So kind of interesting, on average about 120 centimeters or 47 inches is evaporated into the atmosphere from from the ocean each year. So that's pretty interesting how that works, huh? So the energy can come from any source: sun, atmosphere, earth, even humans. So transpiration. Transpiration is evaporation of water from plants. So just another way that the water gets up into the up into the upper atmosphere. Sublimation is when a solid is changed into the vapor, so it skips the liquid phase. So this happens when ice and snow change into a water vapor or a gas. So this is pretty common, constantly happening up in the mountainous areas. Condensation is when a gas is changed into a liquid, right? So we can see that appear as clouds, fogs, mist, dew, or frost, depending on the physical conditions of the atmosphere. Transportation is the movement of the solid, liquid, or gaseous water through the atmosphere. Without the movement, the water evaporated over the ocean would not precipitate over the land. Precipitation is a results when tiny condensation particles grow through collision and coalescence. And then runoff is when excessive precipitation and the ground is saturated, cannot absorb more water. This runoff flows into the streams and rivers and eventually back to the sea. So, and then infiltration, movement of water into the ground from the surface. Groundwater flow is the flow of water underground, and then plant uptake is water driven from the groundwater or flow into a soil moisture. So, just this identifies what that would look like. So you got evaporation, condensation, transportation, precipitation, sublimation, all of those things important for water cycle. I kind of like to tease my daughters. They start doing their jokes on each other and go, well, you all drink dinosaur pee. It's kind of true because the water is same stuff that was here when the dinosaurs were around, right? So anyways, so saturation is when the maximum possible quantity of water vapor that an air parcel can hold at any given temperature and pressure. Once it's saturated, the air parcel has all the water vapor it can hold. And this means, this leads, once it hits saturation, that's when we see precipitation. It starts dumping the water because it can't hold anymore. Relative humidity is the ratio usually expressed as a percentage of water vapor. So you hear people always talk about, in Florida, it's 80 degrees but 100% humidity, you know. It's that's what we're talking about, is the amount of water vapor content divided by the water vapor capacity equals our relative humidity. So it's, like it says here, it's the most common method of describing atmospheric moisture, but it also is the most misunderstood. Relative humidity can be confusing because it does not indicate the actual water vapor content of the air, but rather how close the air is to saturation. An air parcel with 100% relative humidity is saturated, while an air parcel with relative humidity less than 100 is unsaturated. An air parcel's capacity to hold water vapor at a constant pressure is directly related to its temperature. It's possible to change the relative humidity without changing the vapor content. So this is what it's talking about. So a potential gram of water vapor versus an actual gram of water vapor, just change the temperature, and due to the temperature change, we have different saturation levels. Remember, up here on the calculation, it's water vapor content versus water vapor capacity. So temperature plays a huge part in that. Dew point is a temperature an air parcel must be cooled at constant pressure and constant water vapor pressure to allow the vapor to allow the water vapor in the parcel to condense into water. So temperature dew point spread. So the differences between an air parcel's temperature and its dew point is the dew point depression, or commonly referred to as the spread. So this is kind of an important subject here. Okay, in all of our METARs, we will always have the temperature and dew point spread. Okay, when we're looking at that, we're looking to see how close the two temperatures are. When we see the temperatures converge, that typically means we're going to see things like fog or mist form. So the temperature greatly affects the air parcel's ability to hold water vapor, while the dew point indicates the actual quantity of water vapor in a parcel. As the spread decreases, relative humidity increases. And then when the spread decreases to 0, relative humidity is 100% and the air parcel is saturated. Below illustrates the relationship between dew point spread and relative humidity. So same kind of thing, right? Where we've got the temperature difference is the only thing that's actually varying our saturation level. But yeah, when we're watching the weather and we see a temperature dew point spread start to narrow and get to that 0% or 0 degree difference, we need to be watching for that, because we're going to know that at that point likely we're going to be seeing fog or other visibility restricting things. So we need to plan for possible holding and things of that nature. So change of phase, pretty self-explanatory. Latent heat is the quantity of heat energy either released or absorbed by a mass of a substance when it undergoes phase transition. Okay. So during this transition, that's when we have that latent heat. Not super important. More G-golly information. Okay. So let's start talking about clouds. Did you guys watch that video last night of the on clouds?
Yes.
What did you think?
It was helpful to see them.
Yeah. So cloud types will greatly affect, you know, what weather we can expect. So, like it says here, cloud is a visible aggregate of minute water droplets and or ice particles in the atmosphere above the Earth's surface. Okay. So let's talk about the different cloud forms that we see. There are 4 basic cloud forms. We've got cirriform, nimbus, cumuliform, and stratus, right? So cirrus or cirriform clouds are high-level clouds above 20,000 feet and usually composed of ice crystals. High-level clouds are typically thin and white in appearance, but can create an array of colors when the sun is below the horizon. Cirrus generally occur in fair weather and point in the direction of the air movement at their elevation. Okay. So, we call these clouds mare's tails. Pretty easy to see why. My word, why is everything so tiny? So, yeah, I mean, I don't like that.
Are you on your Mac?
Yeah, I mean, I know how to do the whole zoom in thing, but I want to, there we go. Much better. Okay, so there you go. That's a much better picture of a cirrus cloud, right? Pretty easy to see why it's called a mare's tail. We also have this. Some people compare it to like popcorn, right? But you can see that when we see these cirrus clouds form, typically what we're looking at is a high wind speeds at that elevation. Wind's going to be moving pretty quick. And like the reading said, you know, this typically points in the direction of the wind as well. So kind of interesting. But there's some really cool looking clouds out there. So nimbus clouds, Nimbus comes from the Latin word meaning rain, right? So anytime we see nimbo, or nimbus, we automatically associate it to rain, okay? These are the rain-bearing clouds. These clouds typically form between 7,000 to 15,000 feet and bring steady precipitation. As the cloud thickens and precipitation begins to fall, the bases of the cloud tend to lower towards the ground. Okay. Cumuliform clouds are the big old fluffy cotton balls. Okay. Vertical motion, it shows the vertical motion or thermal uplift of air taking place in the atmosphere. The level at which the condensation and cloud formation begins is indicated by a flat cloud base, and its height will depend on the humidity of rising air. The more humid the air, the lower the cloud base. So like I said before, the tops of these clouds can reach over 60,000 feet. We get the towering cumulus, and those are pretty intimidating. So let's look at Nimbus Clouds, right? Pretty ugly looking clouds. When I see the green color, like this picture shows, I immediately start thinking tornadoes. Cancel. I was in Salt Lake when we had that tornado happen, and that really eerie green color got really intense right as the tornado started forming. But yeah, kind of scary. But these are like cumuliform clouds, right? Really fluffy clouds. The reason why we're seeing both the cumuliform clouds and nimbus clouds is typically the cumuliform clouds turn into what we call a cumulonimbus cloud, which means a cumulus cloud that is bearing a whole lot of water. It's a rain cloud, right? This is the start of an anvil top, you can see there, or a towering cumulus. This is what they look like over Salt Lake frequently. We'll talk a lot more about these towering cumulus clouds. But you can see why they're called anvil tops. Pretty intense clouds. Kind of like, looks like the videos of nuclear bombs going off, you know? So, stratiform clouds. So, stratus is Latin for layer or blanket. Cloud consists of featureless, low layer that can cover the entire sky in a blanket, bringing generally gray and dull weather. Cloud bases are usually only a few hundred feet above the ground over hills and mountains and can reach ground level when they may be called fog. Also, as fog lifts off the ground due to daytime heating, the fog forms a layer of low stratus clouds. So, yeah, let's look at some stratus clouds. That's really pretty. Those aren't stratus. It's cirrostratus, but not stratus. So yeah, stratus clouds just nondescript little puffs. I think it's funny. Like, some of these images are anything but a stratus cloud. Ooh. That's definitely not a stratus cloud. We'll talk about those too. But you guys get the point, right? It's kind of a nondescript, low layer of clouds like that. These ones up here, these popcorn ones, so these are what we call cirrostratus clouds. It's kind of a blanket, but they're typically very high altitude. So, do you know what causes this? Ooh. Anybody?
Aliens.
You're close. This is typically caused by airplanes descending through the cloud layer.
This chemtrails?
No, I'll show you chemtrails.
We gotta find out how we dispatch chemtrails.
The government wouldn't let us know if we were, right?
That's just what the conspiracy wants us to think.
Yeah. Yeah, but remember these cirrostratus clouds are typically formed by ice, right? And when an aircraft descends through them, it'll punch holes in the clouds like that. So, kind of interesting. Dude, let's look at some chemtrails. Look at them just crop dusting us, man.
That's how we're getting our polio vaccines now.
Yeah. Oh man, that is freaking cool. I hope that's not fake. I like how they label this chemtrails.
That's like a chem dump.
Yeah. Well, so we're going to talk about this type of cloud. But these are very common near mountains. This is called a standing lenticular. See how we call it that? Kind of looks like a contact lens. Gosh. I shouldn't have looked this up. It's irritating to me for some reason. But gosh. People have way too much time on their hands to think about stupid things. Anyways, yeah, this is due to extremely high winds. Around the mountains, so we call that a 5-stack pancake. I've seen triple stacks. I've never seen a 5 in person, but oh, look at that chemtrail nozzle. Oh no. Sorry. I'm gonna have to show you guys a video. That's just too good to keep to myself. In the airlines, we have a lot of fun with making fun of different things. We're not trying to be malicious or anything, but let's see. Let me pull it up here. I'll paste it into YouTube. You guys can watch it on a break. But you guys know the whole service animal thing. If you need it, great. But it's getting a little out of hand right now. There's people bringing kangaroos, Shetland ponies, peacocks, turkeys, like you name it, somebody's attempted to bring it on an airplane or has successfully brought it on an airplane.
Is it the Chris Pratt video?
Yeah.
I just saw that yesterday. I was dying.
Yeah, it's freaking hilarious. Let's see if I can. All right. There you go. Watch that on a break. It's pretty awesome. But anyways, I've got a couple flight attendant friends that are like getting to the point where they're like, if I have to clean up any more dog vomit or poop or pee on an airplane anymore, or cat or whatever people bring on. I guess in Canada you bring a moose or something. I don't know. They're like out of patience.
To be fair, cleaning airplanes in the evenings, I can't tell you how many diapers I would find in the seat backs.
Yeah, and that's not cool either.
Yeah, I'm just going to change a diaper and just wedge it in there, even though there's a trash can on the way out.
Yeah.
No problem. Someone will get it.
Yep. Yep. I'm not condoning any behavior. I'm just saying.
People are irresponsible.
Yeah.
Moral of the story.
Yeah. And like I said, if you need it, cool. Don't really care personally, but Can definitely fill for my friends. So cloud levels, right? Remember the troposphere, where all the weather is contained, is thins as you reach the poles, right? So that being said, so does our cloud levels. So in polar regions, high clouds would be 10 to 25,000 feet, whereas in tropical regions, 20 to 60,000 feet. Okay. Low clouds, they're pretty much going to be the same across the board because they're low clouds, and the troposphere is a lot taller than 6,500 feet. But yeah, so the different cloud types, so in each level, the clouds may be divided by a type or genre. The definitions of the cloud types given below do not cover all possible aspects, but are limited to a description of the main types of the essential characteristics necessary for distinguishing a given type from another type having somewhat similar appearance. Okay. So like I said before, high clouds, we call those cirrus. So we have different types of cirrus clouds. We've got Cirrocumulus and Cirrostratus Clouds. Typically thin and white in appearance, but can appear to in a magnificent array of colors when the sun is low in the horizon, as we said before. So, so this would be your regular cirrus cloud here. Cirrocumulus would be, oh, that's the popcorn. Okay. So, there you go. Looks like an asbestos ceiling. And then you got the Cirrostratus. Just a thin blanket over the sky, right? So middle clouds are distinguished by the word alto. Latin for middle is alto. So you've got altocumulus, altostratus, and nimbostratus are mid-level clouds. Your altocumulus clouds, just a lower level of your cirrocumulus clouds. But yeah, still kind of that popcorn texture. Altocumulus lenticulars, also known as altocumulus standing lenticulars, are an orographic type of cloud. They appear to be dissolving in some places and forming in others. They also form in patches in the shape of almonds or wave clouds. So these formations are caused by wave motions in the atmosphere and are frequently seen in mountainous or hilly areas. So that's those clouds that I was showing you. Those altocumulus standing lenticulars tend to identify areas of high-speed wind, possible turbulence in the vicinity of those. If you see the altocumulus standing lenticulars as you're flying, general rule of thumb, we just kind of stay away from that area. They typically form, sometimes they'll form directly over the peak. They typically form on the leeward side of the mountain. So you've got the windward and the leeward side of the mountain, right? So windward means that the wind is coming from that side. So you get strong updrafts on the windward side of the mountain, right? Leeward is talking about the backside of the mountain. So what happens if you get a high-speed wind in a mountainous area, you'll get really strong updrafts followed by a really strong downdraft. And this forms what that wave motion. We see it expressed a lot, or you'll hear it referred to as wave turbulence, because it's not like chop turbulence where it feels like you're driving down a bumpy road. Wave turbulence feels like you're riding a wave. You'll descend pretty rapidly, and then you'll climb really rapidly, and then you'll descend, and it's a smooth ascent and descent. Well, that's how the standing lenticulars form. Altocumulus standing lenticulars. Typically, we see them form along the leeward side of the mountains, and we'll see that, and that's due to the wave motion coming off the peak. So kind of interesting. But so altostratus, as you can see here, just that weird layer of gray clouds. Just kind of at a higher altitude rather than right against the ground. So mid altitude, right? Nimbostratus is that gray color, but it is bearing rain, right? So you get that bluish gray color, sometimes that greenish color. So here are low clouds. We got cumulus, towering cumulus, stratocumulus, stratus clouds, and cumulonimbus. So our towering cumulus clouds are, we can have the two forms. This is just a cumulus clouds. Typically form due to convection. You get basically that rotation of air with the moisture present will form this kind of cloud. But when we have a whole lot of convection, it's going to create these towering cumulus clouds. You need a whole lot of convection and then a whole lot of water vapor in the air. But we'll see these towering cumulus clouds form. So these clouds, we associate both the cumulus and the towering cumulus, we associate with turbulence. The towering cumulus clouds, let's see if it talks about it a little bit, but the towering cumulus has 3 stages. You've got your cumulus stage, your mature stage and then your dissipating stage. So as these clouds form, these are indicative of a thunderstorm forming, right? These are typically seen when a thunderstorm is developing. But what's happening is this is like a washing machine inside, like a spin cycle. Extremely dangerous clouds to fly near because of the turbulence, because of that really strong convection. As the cloud forms and builds, what happens is the air is rising extremely very rapidly. And as it reaches these higher altitudes, it's descending rapidly. And then it heats up as it gets closer to the ground and then ascends, then cools and descends. So we get this constant churn of that water vapor. And aircraft are not to fly within 20 miles of these towering cumulus clouds because of how far that convection is felt from those clouds. It's like flying into a tornado, right? It'll chew up the plane and spit it out, no problem. But yeah, when we see a towering cumulus cloud form near an airfield, it has a potential of shutting down that airport. And they'll also be identified in the METAR when we see those, as well as those altocumulus standing lenticulars. They'll be identified in our weather reports because of the type of weather that is usually associated with them. So Stratocumulus Clouds, just this is what we typically think of when we think of Stratocumulus Clouds. So it's just a blanket of cumulus clouds. And then, of course, stratus clouds. So occurs as gray, fairly uniform, featureless single layer of low cloud. So, yeah, stratus fractus or cumulus fractus clouds, typically following bad weather or precipitation. It's just the clouds breaking apart, basically. Cumulonimbus clouds. This is your typical thunderstorm cloud. Still hasn't towered quite yet. When it towers, that's when it gets the anvil on the top. But so let's read about this one real quick. So exceptionally dense and vertically developed, occurring either as isolated cloud or as line or wall of clouds with separated upper portions. These clouds appear as mountains or huge towers, at least a part of the upper portions of which are usually smooth, fibrous, or striated and almost flattened as it approaches the tropopause. This part often spreads out in the form of an anvil or vast plume. Under the base of the cumulonimbus, which is often very dark, there frequently exists virga. So virga, be careful how you spell virga. By the way, I learned that last class. Virga is these little drops, I don't know, little tails of clouds that are descending from the base of those cumulonimbus clouds. Okay. What's happening is it's raining and evaporating as quickly as it's rain that's not reaching the ground, basically. The evaporation is occurring too quickly. But we see that quite often under those cumulonimbus clouds. So last class I got to this point and I was like, let's look at virga, and I typed in VERGA, and in Spanish that's absolutely not what it is in English. So be careful when you're typing that in. VIRGA is the correct word. Correct spelling.
Well, now you have to tell us the translation.
A male chicken.
Oh, I see.
And I pulled that up in Google search, like the image search.
Oh,
and
awesome.
Yeah. I heard about that for the rest of class. But
so you got a picture of a rooster?
Yeah. Several of them. It was bad. Super embarrassing. Teaching fail.
Just tell them it's the shape of a cloud.
Yeah, that's right. Towering cumulus cloud with no anvil. So this is when it anvils out. You can see it's basically hitting the tropopause, and that's what's causing it to anvil out. Once it hits that tropopause layer, there's not enough moisture in the air to continue the build of the cloud, and so that's what causes it to dissipate and spread out like that. So cumulonimbus is composed of water droplets, ice crystals, the latter almost entirely in its upper portions. It also contains large water droplets, snowflakes, snow pellets, and sometimes hail. Liquid forms may be substantially supercooled. Cumulonimbus contains nearly the entire spectrum of flying hazards, including extreme turbulence. So these clouds are also what we associate with hail. And what's happening is the water droplets are, as they continue this process of circulation in the cloud, when they're hitting these higher altitudes, it's freezing. And before it can melt, when it'll reach the bottom of the cloud here and build back up to the top of the cloud and just continue to build those little small pellets until they're, softball size hail or whatever it is, depending on the strength of the cloud and the strength of the convection that's occurring, determines the size of the hail we see. And this is insane, but check this sucker out. It's like 9 inches. Could you imagine that hitting your car? That would suck. Anyways.
Can you imagine that hitting somebody in the head? That would probably kill somebody.
Oh, yeah, for sure. I mean, I've been in like little smaller than golf ball size hill, and it was painful. Like, you got under cover as quickly as you could because it hurt bad. I couldn't even imagine having something that big hit you in the head, you know. Anyways. So, precipitation. Basically, it's just anything that falls from the clouds, right? The necessary ingredients for formation needs water vapor, sufficient lift to condense the water vapor into clouds, and then a growth process that allows the cloud droplets to grow large and heavy enough to fall. Significant precipitation usually requires clouds to be at least 4,000 feet thick. The heavier the precipitation, the thicker the clouds are likely to be. So the growth process. Once again, clouds are water vapor, right? So they all contain water, but some produce precipitation. So clouds, that water vapor is just kind of there circulating, right? As it collides with these other water vapor droplets, it begins to build. If it falls from the cloud, then typically it's evaporated and returns to the cloud, and we have this cycle. Well, as these water droplets start colliding with more and more and more and more of those water vapor droplets, we start to see the formation of the raindrop, right? These raindrops can break apart and form more raindrops until finally they get heavy enough to where they overcome the convection and drop out of the bottom of the cloud. And hail, we see, is because of like I was describing before, the altitude at which those water droplets are reaching, and they freeze. So snow is just where it's colder, right? You get ice pellets that occur when there's a shallow layer aloft with above freezing temperatures and a deep layer of below freezing air based at the surface. So ice pellets or sleet is where It's warm where the cloud is, but colder near the ground. So as the snow falls into the shallow warm layer, the snowflakes partially melt. As the precipitation re-enters air that is below freezing, it refreezes into ice pellets. Freezing rain, bad stuff. So rather than the shallow layer of warm air, you have a deep layer of warm air. And then, of course, rain, right? Got the shallow layer below freezing. As it descends, it warms all the way down to the surface. That completes our presentation. So, why don't we take a 15-minute break, and we'll jump back on at 6:55.
Sounds good.
Alrighty. So, what do we got next on the agenda here? So on day 5 of our week 4, we've got our meteorology discussion here. We're going to talk about fog, ice, stability, instability, and turbulence. So what I want you guys to go in and do first is I want you to watch this stability. Actually, no, let's start with the fog. Watch the video on the different fog types, and then we will jump back on.
Sounds good.
It's about 10 minutes long. All right. Glad you love videos. Because I do too, if you haven't noticed. So, types of fog. So, talked about radiation fog, advection fog, upslope. So, any questions on the different types of fog that we tend to see? The main thing you need to remember about fog is radiation fog typically is going to be calm to light winds, right? Whereas advection fog is it requires the winds, increase of about 15 knots is what it says. So
Because of our minimums, referring to SkyWest, you cannot dispatch into a foggy airport, is that correct?
It depends. Fog doesn't prohibit us from landing. The thickness of the fog layer can bring minimums or visibility down to the point where we can't dispatch to it, but I very frequently dispatch aircraft into quarter-mile, 100-foot ceiling scenarios, or what we call a Class 2 or Category 2 landing. Category 2 landing. So, like I said, it doesn't prohibit us from landing necessarily. What we need to be careful about is the thickness of the fog layer. So as long as we have, and we're going to talk about this more when we talk about the practical dispatch applications, but as long as we have visibility at our ETA when we're planning the flight, and the flight is over an hour long, then that's all we really require. We don't even consider the ceiling because we don't know. When we look at the TAF, which we're using to determine are we legal to go or not, that's a forecast. We don't know if that ceiling is actually going to happen, right? So, and we don't know where that ceiling is being measured from. So, what happens is we can still dispatch, but the pilot, let's say he gets to the destination and the ceilings are reported lower than our minimums, then he can't even start the approach. So he'll sit there and hold, and let's say all of a sudden minimums, we all of a sudden get the minimums. What happens at that point is he can initiate the approach. So as soon as he's initiated his approach into the airport, then it doesn't matter if all of a sudden the METAR changes and says that the ceiling or the visibility is dropped below mins again. If he is on approach, if he's initiated his approach into the airport, he can continue his approach down to the minimum decision altitude. And at that point, he would have to determine, at the MDA, he'd determine whether or not he can see the runway. And if he can, then he'll continue the landing. If he can't see the runway, he'll throttle up and go around. So, yeah, Ash, you're from the Bay Area, right? So, pretty much a daily occurrence for you. But, so advection fog is typically what we see in the Bay Area, or in like Seattle. And you know, that video, I don't really need to add anything to it. We could read all this if you really want to, but it really does a good job of describing how the fog is formed, right? So, you know, something that I thought was kind of interesting that he talked about was his friend in Alaska talking about caribou. Just the caribou's warm breath. You know, they're typically in a herd of 200 plus, but just their warm breath is enough to create fog and reduce visibility. So, kind of interesting. Icing. Okay, this is a huge part of aviation. And we've talked about this several times before now, but let's actually talk about what it is, right? So icing is a deposit of ice forming on an object. It is one of the most major weather hazards in aviation. Icing is a cumulative hazard. The longer the aircraft collects icing, the worse the hazard becomes. So supercooled water. This is like the water bottle trick that I was talking about, where you take a water bottle that's sat in the freezer for a certain amount of time, and you dump it onto a plate, and it turns to ice before your eyes. That's the same thing as this supercooled water. So it's just the surface tension inhibits the freezing. So as soon as that surface tension is broken, then we get instant freezing. These supercooled supercooled water droplets, or large drops, are pretty hazardous to fly into, because as soon as the water hits the aircraft, it instantly freezes and collects on the aircraft. So supercooled water will readily freeze if sufficiently agitated. This explains why airplanes collect ice when they pass through a liquid cloud or precipitation composed of supercooled droplets. So bad stuff. So structural icing is the stuff that sticks to the outside of the airplane. It can be categorized into 3 different types, and I would write these 3 different types down because they are on tests. Rime, clear ice, or mixed. So those are our different types. Okay, so rime icing. Rime ice is rough, milky, opaque ice formed by instantaneous freezing of small supercooled water droplets as they strike the aircraft. Like it says, it's the most frequently reported icing type. So the reason why it's hazardous is because of the jagged texture that it forms. It'll trap air, and that's why it is discolored. It looks like ice cubes do, you know. After you pull them out of the freezer, there's usually that white in the center. We'll have the clear edges with the white in the center. That's a lot what rime ice looks like. I can show you. So, I mean, that's... I don't like it on aircraft that are just chilling on the ground. But that's what it looks like there. Is the just that formation of ice there, the opaque color, really bumpy, jaggedy. Okay.
It's basically like the frost on your windshield, only this is much more exaggerated.
Mm-hmm. So let's take a quick look at clear ice. Let's knock out some ice types. Oh, there's a good picture of rime ice. There you go. It's bad stuff. How's that airplane still flying? I'm not seeing a good example of the clear ice. You can see it there behind the boot. That's your clear icing. Okay. So clear ice is a glossy, clear, translucent ice formed by relatively slow freezing of large supercooled water droplets. So occurs more often in in warmer temperatures, high liquid water contents, and larger droplets. So forms when only a small portion of the drop freezes immediately, while the remaining unfrozen portions flows or smears over the aircraft surface and gradually freezes. Few air bubbles are trapped during this gradual process. Thus, clear ice is less opaque and denser than rime ice. Okay. So we already talked about these supercooled large droplets. Mixed ice. So it's a mixture of the clear and the rime ice. Collects both rime and clear ice due to small scale variations in liquid water content, temperature, and droplet sizes. Okay. So just a mix of the two different types of icing, and it's formed because of the variations that we encounter in aviation. If there's a rapid variation, we'll likely see this mixed ice. So icing factors. Structural icing is determined by many factors. The quantities and the severity, and then those are how we list them in order of importance. So sorry, icing type, severity, okay, quantity, icing type, and severity. So you'll see light rime, and things like that in our pilot reports. Okay. So for icing to occur, the outside air temperature must be 0 degrees Celsius, which is not what we play by in dispatch. In dispatch, what constitute icing conditions? Anybody remember?
Isn't any kind of moisture in the air?
Yeah, what temperature?
Isn't it 10 degrees Celsius?
Invisible moisture, right? Or visible moisture, and 10 degrees Celsius. So anything 10 degrees Celsius and below, we consider icing potential. So icing in stratiform clouds. Icing in the middle of low-level stratiform clouds is confined on average to the layer between 3,000 and 4,000 feet thick. Thus, a change in altitude of only a few thousand feet may take the aircraft out of icing conditions. Okay. So what happens if we're in icing conditions? Get above the cloud or below the cloud, right? And that's for stratiform clouds. If it's cumuliform, typically the clouds are taller than they are wider, so we will change our course to get out of the cloud, right? Icing with fronts. Most icing reports occur within the vicinity of fronts. This icing can occur both above and below the front. For significant icing to occur above the front, the warm air must be lifted and cooled to saturation at temperatures below 0. making it contain supercooled water droplets. These supercooled water droplets freeze on impact to the aircraft. A line of showers or thunderstorms along a cold front may produce icing, but only in comparatively narrow band along the front. Okay. So there you go. So typically where we're going to occur, or where the icing is going to occur is right on the edge of that front and directly above the high pressure or cold front. So, favored location for severe clear icing is freezing rain and or freezing drizzle below a front. Okay, so this is where you don't want to be. Severe icing, if you guys remember in the FARs, no person may dispatch an aircraft into severe icing. So what that means is if there is severe icing being reported, we can't fly anywhere near that. If certain types of precipitation is falling over our destination airport, we can't even dispatch to that airport due to the icing hazards. So as far as being able to dispatch into certain precipitation types, that's going to be published or determined by the airline that you're flying with and the aircraft. So, but basically, we want to stay out of anything that has the potential for severe icing. Don't want to be anywhere near the ground when that potential is there. So icing is more likely and more severe in mountainous regions. Mountain ranges cause upward air motions on the windward side. These vertical currents support large supercooled water droplets above the freezing level. The movement of the front across the mountain range combines frontal lift with the mountain's upslope flow effect to create extremely hazardous icing zones. Okay. So just like we were talking about before, windward, leeward side, right? So the greatest potential for icing is on the windward side due to the rapid rising of the air here, creating those larger supercooled water droplets. The most severe icing occurs above the crests of the ridges on the windward side. So zone usually extends about 5,000 feet above the mountain tops, but can extend much higher if cumuliform clouds develop. So why is it hazardous? So it degrades the aircraft performance. It destroys the smooth flow of air, increasing the drag while decreasing the ability for the airfoil to create lift. So you're getting a double whammy here, right? The actual weight of the ice on the airplane is insignificant when compared to the airflow disruption it causes. As power is added to compensate for the additional drag and the nose is lifted to maintain altitude, the angle of attack is increased, and this allows the underside of the wings and fuselage to accumulate additional ice. Okay, so pilots, when correcting for icing, they're trying to maintain their altitude, right? That's what they're doing. Is a lot of times they'll increase the thrust and then change their pitch to maintain the altitude. Well, that just increases the problem. So, wind tunnel and flight tests have shown that frost, snow, and ice accumulations on the leading edge or upper surface of the wing, no thicker or rougher than a piece of coarse sandpaper, can reduce lift by 30% and increase drag by up to 40%. That's what I was talking about before when my buddy was taking off. One wing had been in the shade and got a little dew on it that froze. Looked pretty insignificant, but as they took off, it caused the aircraft to roll pretty dramatically. And luckily they were able to save it, but pretty intense. 30% and reduction of lift and a 40% reduction or increase in drag. That's pretty significant. Larger accretions can reduce lift even more and can increase drag by up to 80% more or more. So, super bad stuff. So ice accumulates on every exposed frontal surface of the airplane: wings, propeller, windshield, antennas, vents, intakes, and cowlings. It can build in flight where no heat or boots can reach it. It can cause antennas to vibrate so severely that they break, and then in moderate to severe icing, a light aircraft could be subject to enough ice accumulation and accretion that continued flight is impossible. So it can cause the aircraft to stall at much higher speeds and lower angles of attack than normal, and it can roll or pitch uncontrollably, and recovery might be impossible. So we're gonna read through an NTSB investigation on an aircraft that had flown up from Florida to JFK, and it was icing conditions in JFK, and the pilot made several mistakes, and then ended up crashing the aircraft. It wasn't in JFK. It was Dulles, so in Washington D.C. Ended up crashing the airplane into the Potomac. But yeah, icing's bad stuff. We're not going to talk about carburetor icing. Doesn't really have an effect on us, but because we don't have carburetors and jet engines, believe it or not. All right. So this high ice water content So under certain high ice water conditions, turbine engine performance can be affected, including flame outs. So that's why we have that engine cal anti-ice, is because of the this high ice water content getting sucked into the engines. A flame out basically it's where the combustion stops occurring in the engine, and it's really hard to restart an engine when it's flamed out. So it can have the potential of losing an engine. Kind of already talked about all that. I'll cruise through that, save you guys some brains. So, I'm trying to think. Hold on just 1 second. right, sorry about that. All right, so let's talk about orthographic lifting here, orthographic effects. So wind blowing across mountain valleys causes moving air to alternately ascend and descend. If the relief is sufficiently great, the resulting expansional cooling and compressional warming of the air affects the development and dissipation of clouds and precipitation. So exactly what we were talking about before. Leeward side, windward side, or I'm sorry, windward and leeward side. So the moist air tends to be on the windward slope. This is where we're going to see the upslope fog, the cumuliform clouds forming, cumulonimbus. A lot of times this is where most of the precipitation is going to fall, is at the footing of the mountain, right? So so that's all it's talking about there. So frictional effects. So in the northern hemisphere, the surface wind spirals clockwise and outward from a high pressure, and counterclockwise and inward into a low pressure due to frictional force. Okay. End result is that winds diverge away from the surface high pressure, causing the air to sink, compress, and warm, which favors the dissipation of clouds and precipitation. Conversely, the wind's coverage into the surface low pressure, causing the air to rise and expand and cool, which favors the formation of clouds and precipitation, giving sufficient moisture. So what we need to remember here, and I've said it a couple times now, high pressure rotates clockwise and down. Low pressure rotates counterclockwise and up. Okay, that's why we get the cloud formations on the edge of the low pressures. So frontal lift. So this occurs when the cold, denser air wedges under the warm, less dense air, plowing it upward, and the warmer air rides up and over the colder air in a process called overrunning. The cloud and precipitation will form, giving sufficient lift and moisture content of the warm air. So here you have the high pressure pushing underneath the warm or low pressure, and that's exactly why we see that precipitation or the storm systems that we were talking about. The cold air causes that warm air to rise much more rapidly. So buoyancy. Basically, the air near the ground can warm at different rates depending on the insulation properties of the ground in which it's with which it's in contact with. So depending on the type of ground, it can warm or cool at different rates. And the temperature difference results in different densities, allowing the warm air to become buoyant. Okay. The denser cool air will tend to push the less dense warm air aloft. On a ground scale, the tendency of the air to rise due to heating and how high it will rise is referred to as stability. So, atmospheric stability. This is where I want you guys to watch this this video. Where did it go? Crap.
I tried to find it earlier and it wasn't posting.
research here. So, here you go. So everybody watch that video, and when it's done, we'll jump back on. This one's about the same amount of time, so. Okay. So atmospheric stability. So stability types. We've got absolute stability, okay? State of column of air in the atmosphere when lapse rate of temperature is less than the moist adiabatic rate. So an air parcel lifted upward would be colder or more dense than the surrounding environment air and would tend to sink back to its level of origin. So this is what an absolute stability would look like. Parcel of air would rise and fall right back to the same temperature. Where there's temperature difference, we would not see the moisture in the air. So as we move on here, neutral stability, state of a column of air in the atmosphere in which the ascending or descending air parcel always has the same temperature as the surrounding environment air. If the column of air is unsaturated, then neutral stability exists when the lapse rate of the temperature equals the dry adiabatic lapse rate. If the column of air is unsaturated, then neutral stability exists when its lapse rate temperature equals the most moist adiabatic lapse rate. Okay. So as you can see, the difference between the two, absolute stability is when it's just a column of air, an air parcel, right? Either side of the air parcel, you have temperature differences or dew point differences. But here we'll see that the parcel of air will match its environmental air temperature. Okay. All right, so absolute instability is a state of column of air in the atmosphere when the super adiabatic lapse rate of temperature, an air parcel, when it has the super adiabatic lapse rate of temperature. An air parcel is displaced vertically and would be accelerated in the direction of the displacement. The kinetic energy of the parcel would consequently increase with increasing distance of its level of origin. So we have this extremely unstable parcel of air, right? So kind of French here, right? All this different types of stability and instability. So what we're really concerned with here is what is the dry adiabatic lapse rate, right? In dispatch, we only use one of these. So this is just talking about, whether an air parcel would be considered stable or unstable and what constitutes it. All of this just kind of is more of a how do you put it? More just informational rather than necessary information. So let's not confuse the crap out of you guys. Sorry.
Is this what we call fill?
Phil?
F-I-L-L?
What is that?
It's what you do to meet the time requirements.
Yeah, pretty much.
Because I'm not sure that, I mean, if it's, did everybody else get that? Because
No.
I'm not sure I did.
Yeah, so what?
I guess what I'm saying, Garrett, is this stuff that we're going to need for?
No, it's just more hitting the requirements.
Okay.
Really, what you need to know is what was in that video, as far as, you know, dry adiabatic lapse rate, moist, you know. Really, the only one that we care about would be the dry adiabatic lapse rate, or the standard adiabatic lapse rate of 2 degrees per 1,000 feet. In dispatch, that's what we plan with. So that's where we started talking about the ISA and ISA deviation. So let's kind of
Didn't mean to put a speed bump in there, but I'm just trying to figure out if
it was necessary, because this is like much higher level. So when we dispatch, we're going to dispatch using, let me go back right here. Okay. We use the standard adiabatic lapse rate because when we're looking at an overview of the entire country, we're going to see just that. I mean, we're not going to be able to see, is this a moist, or we're not looking, is this unstable, is this stable, is this, we're not really looking at that. What we need to know is the lapse rate, and that's due to being able to understand where we may see the weather occurring, or where, you know, in the case of a no icing aircraft, when can we expect icing conditions to occur? So if we look at the standard lapse rate, we don't have time when we're dispatching to go in and, you know, pull a whole bunch of calculations and try to come up with, you know, well, technically we should be using the moist adiabatic lapse rate for this of 3 degrees Celsius per 1,000 feet, because, you know, we don't have time for that. It's nice to know, but it's not necessary. So I highly recommend you guys going back through this material and try to absorb as much of that part as you can. But really what we want to know is that standard adiabatic lapse rate. So when we talk about the standard adiabatic lapse rate, we're talking about the 2 degrees Celsius per 1,000 feet. Okay. And this is where we were talking about ISA. So as we pretend this is mean sea level or 0 feet elevation, here we have 1,000 feet, 2,000 feet, 3,000 feet. So for every 1,000 feet, 1,000, it becomes 2 degrees colder. Okay. So as we ascend, the standard rate is 2 degrees. We lose 2 degrees C per 1,000 feet. So 2,000 feet will be 4 degrees colder than standard. 3,000 feet, will be -6. And this is from the standard temperature. So we have our standard temperature of 15 degrees C at MSL. And I'm really sorry. I wish I had like an Apple Pen or something to where I could actually make this legible for you guys. But so 15 degrees, if we wanted to know what to expect at 3,000 feet, we'd take 15 degrees and we'd minus the 6 degrees off here. That would give us 9 degrees Celsius. This is our standard temperature at 3,000 feet. Okay. 9 degrees Celsius. Okay. So where this comes into play, and I hope you guys are remembering this from our previous lesson, is let's look at St. George Regional Airport here. So St. George is at 28. Let me zoom in here. Okay, St. George Regional Airport is right here. This is the field elevation right here. Okay. Another place that we can see that is not on this page. But we can see it in our Jeppesen charts when we pull those up. Okay, so 2884. So, that being said, what we can do is, let's say, so 2.8 thousand feet. Okay, so let's say that we wanted to know what our ISA deviation is because we want to know how the engine is going to perform in its climb. So what we need to do is we need to figure out what is our standard temperature at 2.8 thousand feet. So all we do is we take that 2.8 and we multiply that by 2. Okay. So that gives us so 5.6. So 5.6, 15 degrees C minus 5.6, oops, equals 9.4. Okay, 9.4 degrees. That's our standard temperature at St. George Airport here. But we look at the METAR and it is 22 degrees Celsius in St. George. Okay, all we're going to do is figure out the difference between the two. Okay, so let's just, for sanity's sake, we're just going to round this. We'll round it up. Oops, I'm sorry. We'll round it up. So when I say in aviation, when I say round it up, we're going to penalize it. Hold on. So if we're penalizing it, warmer temperatures penalize the aircraft performance more. Okay, so we're going to round up to 10 degrees Celsius. 10 degrees Celsius minus 20, or 22 degrees Celsius minus 10 degrees Celsius equals 12 degrees Celsius. So we know that it is 10 degrees warmer in St. George than standard temperature. Or sorry, 12 degrees warmer in St. George than standard temperature. So that being said, we are warmer, so we add a plus sign there. ISA plus 12, okay? So when we look at our aircraft performance charts, we're going to look at ISA plus 12 or the next warmer chart, okay? That's what we really need to take away from this. All that other stuff is like meteorology 1300. So yeah, I mean, if you really like, and I'm not going to discourage it, go through and try to make sense of it. Pull up Bill Nye videos, whatever you got to do. But make sure you have a solid foundation of the things you need to know prior to going on that search. So, turbulence. Let's talk a little bit about turbulence. So what causes turbulence? Convective currents, right? The other thing that we can see that causes turbulence is obstructions or wind shear, okay? So when we have obstructions like buildings near the ground, we're going to see this we call it mechanical turbulence. This convective turbulence, that's going to be those thermal pockets, the pockets of rising air. And then wind shear typically occurs close to the ground. It's when there's an abrupt change in direction and speed of wind. Which causes that turbulence that we all know and love. So convective turbulence, like I said, it happens in vertical motions. It's most active in the warm summer afternoons when winds are light and heated air at the surface creates shallow, absolutely unstable layer within which bubbles of warm air rise upward. So a lot of times we're going to see this convective turbulence in areas where we're seeing, cumuliform clouds and things like that. Sometimes we'll see it, or it'll occur in clear air where there's not any cloud cover. But most of the time there's going to be some weather that's going to indicate, we're probably going to experience some bumps. Okay. And it's just that uneven heating of the Earth's surface that causes this. So, like I said before, a lot of this is occurring near or around these cumuliform clouds. So when the air is too dry for cumuliform clouds to form, convective currents can still be active, and this is called dry convection or thermals. So this is the other type that I was talking about, right? But those thermals, like I said in previous class, those are what, the gliders, turkey vultures, hawks, those are what those are riding and allowing, it's generating lift. In a glider, the maximum distance that a glider's been flown is something like, man, I can't remember. There was a glider flight that lasted like 14 hours or something. And you just catch these thermals and ride them up to higher altitudes. It's pretty impressive for, not having any propulsion system on the aircraft. Let's see, longest. Let's see. 1,023 miles. Pretty insane. So, anyways, yeah, sunrise to sunset. Or 1,023 miles or whatever that guy flew. Pretty insane. Just riding these thermal pockets. So mechanical turbulence is just what I was telling you guys before. The wind is hitting the buildings, which creates its own. You even get it from rotor downdraft or rotor wash. Basically, it's creating its own turbulence. It's a man-made object creating its own turbulence. Another type of mechanical turbulence would be mountain wave. So mountain wave occurs so it develops on the downwind of mountains, so the leeward side. The waves remain nearly stationary while the wind blows rapidly through them. They may extend as far as 600 miles or more downwind from the mountain range. Mountain waves frequently produce severe or extreme turbulence. Location intensity varies with characteristics. Incredibly vertically propagating mountain waves have been documented up to 200,000 feet and higher. That's crazy, huh? So as I was telling you guys before, we get these cap clouds. And then on the backside, we get these alto cumulus standing lenticulars, or the cirrocumulus standing lenticulars. Okay. The really dangerous cloud that pilots don't like at all and avoid like the plague are these rotor clouds. Rotor clouds, think of it like a truck bed, right? What happens is, let's say this is the cab of the truck. As the wind comes over, it dives down into the bed, and here's the tailgate right here, right? Creates this rotor force where the air will just sit there and circulate. When there's any water vapor in the air on in that circulation, it forms what we call that rotor cloud. You can actually watch these rotor clouds churn. Let's see. Let's see. Where's a good one? I mean, that's a pretty good picture, but I was hoping to get a little more than just that up close. But these rotor clouds get pretty violent. There you can see some of the rotors back there. Cap cloud, alto cumulus, standing lenticular rotors. So, extremely dangerous, right? So, that's kind of wicked. Pretty dangerous. So mountain waves often produce violent downdrafts on the immediate leeward side of the mountain barrier. Sometimes the downward speed exceeds the maximum climb rate of the aircraft and may drive the aircraft into the mountainside. Mountain wave cloud is a cloud that forms rising branches of mountain waves and occupies the crest of the waves. So that's the alto cumulus standing lenticulars, or the Cirrocumulus standing lenticulars. There's your rotor. It's a pretty good picture there. So wind shear turbulence. So wind shear is the rate of change in wind direction and or speed per unit distance. Wind shear generates turbulence between two wind currents of different directions and or speeds. So basically what happens is it just creates this nasty pocket of crazy wind. So once it hits that, you may have wind direction and speed shifts of 10, 15 knots, going from a direct headwind to a direct tailwind, which will push the aircraft down into the ground. So very dangerous stuff. So temperature inversion. This can cause that wind shear turbulence as well. Sometimes that cold air is moving in the opposite direction of the warm air. We get that wind shear turbulence. Clear air turbulence. So this is at higher altitudes, the turbulence phenomenon occurring in cloud-free regions associated with wind shear. So this, we're going to see clear air turbulence on the edges of the jet stream. Okay. A lot of times when we have aircraft flying near or perpendicular to a jet stream, they'll oftentimes experience that clear air turbulence. So when we see, I can pull up and see where the jet stream is. If we're planning a flight that's going to be going right through the jet stream, perpendicular to it, I tend to give them a little extra fuel because they'll likely experience turbulence. And the only way to avoid it is to change your flight level. So turbulence factors, how the aircraft responds to turbulence varies with a couple of different factors. Intensity of the turbulence, the aircraft size, wing loading, airspeed, and aircraft altitude. When the aircraft travels rapidly from one current to another, it undergoes an abrupt change in acceleration. So, kind of to help you understand that, a lot of times you'll see PIREPs or pilot reports pop up for turbulence. You'll get a turbulence report. But when you look at it, you'll get a severe turbulence report, and you'll look at what type of aircraft is reporting the turbulence. A lot of times you'll see, Cessna 182 reporting severe turbulence in an area at 10,000 feet or whatever. That isn't going to affect a large jet like a CRJ nearly as much, mostly due to the size. So think of turbulence as like rough seas, right? If you've ever been on a ship, let's say a cruise ship, a lot of times when there's rough seas, the variation and the effect of those waves is minimal, right? You can feel it, but it's not, life-changing effects. But I'll get on, my father-in-law's boat, be out in Bear Lake and hit a 4-foot swell, and it like rocks my world. It's the same thing with airplanes, right? You have these bigger aircraft, they ride those waves a lot better than these smaller aircraft. So it doesn't affect them as greatly. So when we're looking at turbulence reports, we want to make sure that we're associating turbulence with the proper, and we're going to, take it into consideration. But severe turbulence to a Cessna 182 to CRJ, that's going to feel like light chop. That's how the difference is going to translate most of the time. So we take into consideration like aircraft size, the speed as well. Going slower through mountain waves going to exaggerate it a lot more than going through it at 500 knots. So we just need to take that kind of stuff into consideration when we're looking at these reports. So what I want you guys to do is watch this video about turbulence here. And then once you're done watching that video, we'll be done with class. So if you guys have any questions or anything, I can just stop the recording now, get it converted and on YouTube. But if you guys have any questions, please let me know. And if not, I'll let you watch the video. And then just when you're done with the video, we'll be done for the night. So. No questions? What about a study? Does anybody want to do a meetup anywhere or this weekend or? This weekend's a bad weekend.
If anyone wants to come down to Kingman, I'll take you to the boneyard and we can study for the ADX together. It's only a 4-hour drive.
Yeah. Last time I was in Kingman, I thought I was going to get jumped by about 50 bikers.
I feel that way all the time.
Yeah. All right.
In a week in Kingman. Say, I spent a week in Kingman one day.
There you go.
Let me tell you about my 2.5 years.
Well, if anybody needs, needs anything, has any questions or anything, please let me know. If we can get 4 or 5 people to meet up, we can meet up if you guys would like, and just study. We could even do it online so that people that aren't there can join in, but if not,
are we able to go over any ADX stuff?
I mean, sure, but it's really hard to go over ADX stuff because of the nature of the test.
I agree. I've been trying.
Yeah.
Things that I wouldn't mind reviewing, Garrett, regarding the ADX. I'm going through weather right now in preparation, and it's learning how to read those, each one of the reports, the METARs, and what each area. I mean, it would be extremely helpful to have that kind of information sometime soon.
Yep. So that's going to be, I believe that's our next lesson. Let's see. Nope. So that'll be on Tuesday, it looks like. Most likely.
Be helpful.
Yeah, so Tuesday we'll go over weather reports. But we'll get really familiar with them. Promise you that. And I've actually been saving METARs and TAFs and NOTAMs for you guys. So as I see good ones, I save them. But yeah, if there's no questions or nothing you guys want to discuss, then I'll turn you guys loose to watch the video, and we'll see you guys on Monday.
Thanks, Garrett.
Have a good weekend.